Today we're going to learn about solving two-dimensional motion problems. So these are our problem-solving steps. The first thing we need to do is draw a picture and establish positive directions. Since we're working two dimensions, you're going to need to establish a left or right positive direction, so an X direction positive direction and a Y direction positive. Then you need to establish your origin, just like you did in one-dimensional motion problems. You're going to separate your X and Y direction givens into an XY chart. I'm going to show you how to make this. This will help you keep your X direction motion and Y direction motion separate. You learned in class that the X direction velocity stays constant because if we were to draw a force diagram on the object, we just have a force of gravity acting down. It is in free fall. Force of gravity is the only thing acting on it. We are neglecting air resistance. So since we only have the force of gravity acting down, the net force in the X direction is 0. So then the velocity will be constant in the X direction. But in the Y direction, it's going to accelerate at negative 9.8 meters per second squared, or whatever the acceleration due to gravity is on the planet. Then you're going to split your velocity vector into X and Y components. So if this thing is projected upward or downward, you've got to split that into components. You'll select equations to use and write them down without plugging in values. Then make sure you rearrange your equations to isolate for your unknown variable before you plug in values. And then you plug in numbers and solve. Make sure you have units on your answers and then repeat as necessary. Most of the time, you're going to have to either solve for something in the X direction and then plug it in the Y direction, or solve for something in the Y direction and plug it in to an X direction equation to solve for something else. So these are usually two-step problems at least. Also, it's important to make sure that you stay in variables until the very end, because there will be times where you'll have to actually use a system of equations and combine an X direction equation and Y direction equation together to solve. I have a few tips here for you. If something is being launched on level ground and lands on level ground, delta Y will be 0. So this is not often stated, but it'll just say something like a soccer player kicks a ball in a field. So you're just assuming that the ball's going up and coming back down to the same place, and so your delta Y is 0. If delta Y is 0, the maximum height occurs halfway through the time interval. So a lot of times you'll be asked for like the maximum height, how high something goes. And if delta Y is 0, then you have the same amount of time up and the same amount of time down. So you know that halfway through you're at the maximum height because you have the same acceleration the whole time. If delta Y is not 0, that's not the case, so be really careful. If delta Y is 0 also, the initial velocity in the Y direction is equal to the negative of the final velocity in the Y direction. So I should put little vectors over those, which are hard to type in. So that also we've talked about in our one-dimensional motion stuff, where if we have a velocity on the way up, it slows down at negative 9.8 meters per second squared till it stops, turns around, goes back down and accelerates at the same rate for the same amount of time. So your speed will be the same, just the opposite direction. So there's your initial velocity and there's your final velocity. If the object is launched horizontally, the initial velocity in the Y direction is going to be 0 because it isn't projected up or down. So you just got initial velocity of 0. Time is the same in both directions. This is a really important thing to make sure that you remember. It's in the air for the same amount of time in the X direction and the Y direction, and that's going to be helpful for when you're doing a system of equations later, and also you can solve for time in the X direction and then plug it in the Y direction and solve for something else there, or the other way around. Also, on the top of the projectile, Vy is 0. Be really careful here because a very common thing to think is that Vx is 0 as well. But it keeps moving in the X direction, but Vy is 0. And if you are not given an initial velocity, then you're going to plug in for Vx v cosine theta, and for Vy, V sine theta. And then you'll use that system of equations that I was talking about. And I'll have another video for how to do that later. So let me just show you how you would find your components for your velocity. Let's say that you have a velocity like this, and this is your theta, and this is your velocity. So this is your V initial in the y direction, which is going to be V times the cosine, sine of theta. And then this is your Vx, which is constant the whole time, and that's going to be V cosine theta. Okay, the next thing that I wanted to do real fast is to draw a motion map for a projectile that's going in an arc. So we would draw our dot here, and then we would draw our velocity arrow. I will often draw a velocity initial in the y direction, so that's our Vy, and then our Vx is going to be to the side, and then we can draw our total velocity arrow, which is here. So this is Vx, and this is V. And then our next dot here, we make by, I usually just put it at the end of my velocity arrow. So my Vx stays constant, so I should draw that arrow the same. My Vy is going to get shorter because it is slowing down in the y direction. So there's my Vy, and then this is my V here. My total velocity. Here's my next dot. My Vx is constant. My Vy gets a little shorter. And then I have my total velocity. And then at the top here, at the very apex, we just have velocity in the x direction. So Vx and V are the same thing. Because your Vy is 0, but your velocity in the x direction is still constant. The object is still moving to the right at the very top. And then we basically go back down. I made that a little bit too long. So we'll have our Vx and Vy and V, and then our Vx stays constant. Notice that our Vy is, I'm not making this exactly symmetric, but we should have, if we have a positive V here, we have a negative V here. And so forth. So the point there is Vx stays the same, Vy gets shorter and then longer. And then we could also draw acceleration arrows on these. So I would show my acceleration arrows like this. And I would draw them right next to there, showing that the acceleration is down. An important part here is velocity in the y direction up here is 0, but the acceleration is not 0. Sorry, that one's a little. Okay, so all of those acceleration arrows are supposed to be the same. I know they're not perfect. All right, so there's a motion map for projectile motion. Let's give an example. So we have a tiger. It leaps horizontally from a 2.5 meter high rock with a speed of 3 meters per second. How far from the base of the rock will she land, and what is her final velocity? So we're going to sketch the situation real fast. This is not art class, so you don't have to, wow, and drawing on this thing makes my tiger look really good. So, you know, just sketch something real fast, right? And then she's going to come off the cliff and jump like this. And she's jumping off horizontally. Excuse me. So then we know that the cliff is 2.5 meters high. And we know that her velocity, her initial velocity is 3 meters per second. Now, since she's jumping horizontally, that velocity is only in the x direction. The initial velocity in the y direction is 0. we want to know how far she lands from the base of the cliff. So that's going to be delta x. How far does she go in the x direction? And we also want to know her final velocity. Now, it's important to note that when it asks for final velocity, velocity is a vector. So we need to figure out the speed and the direction. So make sure you don't forget to do that. Now we have to set an origin. I'm going to set the origin right here, and then I'm going to choose up and to the right as positive. Okay, so next we're going to fill out our XY chart with our knowns. So we know that our delta y is going to be negative 2.5 meters. And I say negative because the tiger starts at 2.5 and goes to 0. So final minus initial will be negative 2.5. Then the speed is in the x direction, so that's Vx, and that is equal to 3 meters per second. And then we know the initial velocity in the y direction is 0 because the tiger is leaping horizontally. And we know that the acceleration is negative 9.8 meters per second squared because the tiger is on Earth. So that is what we know. And we need to figure out how far from the base will she land, so delta x. And we also need to know final velocity. So we know the final velocity in the x direction will be 3 because it doesn't change, but we'll need to find the final velocity over here eventually. Notice that in order to find how far the tiger goes, we need to find time. And this is usually what's happening in two-dimensional motion problems. You use one of the sides of your chart to find time, and then you plug it in on the other side to find something else. It's really important to remember that on this side of the equation, it's constant velocity. So the equation that you're going to be using is velocity equals displacement over time. Over here, we have accelerated motion. So you're going to use the 4 equations that we learned in chapter 2. So those are delta x equals 1/2 at squared plus v initial times t. And I didn't put all these vector symbols on here. This is average velocity or constant velocity. We have delta x equals 1/2 times v initial plus v final times t. We have v final equals v initial plus acceleration times time. And we have v final squared equals v initial squared plus 2 times acceleration times change in position. Now, the change in position here is going to be a y. Actually, these are all going to be y's. I probably should have made them y's because this is the y direction, right? So I'm going to change these all to y's. And we're going to use x to show change in position in the x direction and y to show change in position in the y direction. Okay, so we're going to use those equations for that side. So the first thing we're going to do is solve for time here. And to do that, we pick one of these equations. So I have displacement in the y, I have initial velocity, I have acceleration, and I need time. I don't have v final, so I'm going to pick the equation that doesn't have v final in it, which is the second one. I'm going to use delta y equals 1/2 at squared plus v initial times t. And my initial velocity is 0, so that goes away. And I'm solving for t. So I'm going to multiply by 2, divide by a, and square root. So I get t equals 2 times delta y divided by acceleration, and then we square root. And then I can plug in numbers. My delta y is negative 2.5 meters, and my acceleration is negative 9.8 meters per second squared. If you ever get a negative time or a negative under the square root, go back and look at your numbers because you've probably just made a mistake. So when we do that with you made a mistake with your signs. So when we do that, we get a time of 0.71 seconds. That's our time. Now we're going to use that time to plug it on the other side. So now we know that, I'm just going to put an arrow here. Time is equal to 0.71 seconds. So now we can figure out the displacement in the x direction, which I'm going to rearrange this equation as velocity times change in time. So change in position is equal to 3 meters per second times 0.71 seconds. And we get 2.1 meters. All right, so there's the first part. The next part is finding the final velocity. So I need to use these equations to find final velocity. I can use any of them at this point because I have all the other knowns. However, I would recommend that you try to use your initial knowns for everything if you can. You can't always, but if you can, like in this case, if there was a mistake in this calculation and I used this time to calculate final velocity, then I would have a mistake there too. But if you use your initial givens, then you may not have that situation. So let's use the equation v final squared equals v initial squared plus 2a delta y. And we're solving for v final and v initial is 0. So we'll write it as v equals the square root of 2a delta y. Then we'll plug in some numbers. So we get 2 times the acceleration, which is negative 9.8 meters per second squared, times delta y, which is negative 2.5 meters. And that gives us a velocity of negative 7 meters per second squared. Now we have to be careful here because, no, not squared, sorry, meters per second, we're solving for velocity. Okay, so we have to be careful here because our equation is square root, and so the answer could be positive or negative 7 meters per second. We have to make the decision on if it should be positive or negative. And since I chose up as positive, it needs to be negative 7 meters per second. And this is the final velocity in the y direction. So that's actually not my final answer, so I'm going to undo that little circle there. And now we need to find the total final velocity. So we can draw a little triangle, which I think is the easiest way to do that. The ball is moving 3 meters per second to the right, or ball, tiger, and then she's moving 7 meters per second down. Now you're not going to put a negative 7 here because the direction is going to be given with an angle, not with a sign, since it's moving some to the right. She's moving some to the right and some down. So we would find this velocity, which is our final velocity, by doing the square root of 3 squared plus 7 squared. We're just doing Pythagorean theorem there, which gives you 7.6 meters per second. And then we have to find the angle. So we're going to use trig to find our angle. So we get theta equals the tan inverse of 7 over 3, which is 66.8 degrees. So our answer to this question is the tiger is moving 7.6 meters per second at 66.8 degrees below the horizontal. So when you're giving directions for projectile motion problems, you're going to be given the angle with the ground, basically. So we can say below the horizontal. Okay, so there's one question. Now let's try another one where there is an initial velocity that is not 0 in the y direction. So in this case, we have this kid throwing a ball, and the initial velocity is 10 meters per second. It's thrown at 50 degrees. So what that means is that this angle right here is 50 degrees. It is also thrown 2 meters above the ground. So this distance right here is 2 meters. And I'm going to choose right here as the origin. I need to do up and to the right as positive. All right, so we've set up the problem. We need to know how high the ball goes. We need to know how far the ball goes. We need to know how much time it takes. And then we need to know the final velocity. We got a lot of things to figure out. So the first thing that we need to do is, before we make our XY chart, is split up our velocity into components. And if you have the velocity components, you can just, or the velocity and the angle, you can just do that right now. So this is 50 degrees, and this is 10 meters per second. So this is the initial velocity in the y direction, and that's going to be equal to 10 times the sine of 50 degrees. So that gives us, I cannot read my printout. Let me redo my calculation there just to make sure I have the right answer there. So that's 7.6 meters per second. 7.7. And then the x direction velocity is equal to 10 times the cosine of 50. And so Vx is equal to 6.4 meters per second. All right, now we go down to our XY chart and we can lay out the things we know. We know in the x direction that the velocity is 6.4 meters per second. And that's all we know. In the y direction, we know the initial velocity in the y direction is equal to 7.7 meters per second. We know the acceleration in the y direction is negative 9.8 meters per second squared. If we're thinking about the entire time, we do have to do y max. So y max is not the entire motion of the ball. So I think we're going to come back to that one and do that one last. We can find these three are all for the entire motion. So let's do those first. So for those, our delta y would be negative 2 meters. It starts at 2 meters and it goes down to 0. So 0 minus 2 is negative 2. And that's what we know. So now we are going to use this stuff to solve for time, and then we can plug it in the x direction, which is our common method. So I have these equations and I need to solve for time. Now, the only equation without v final in it has, it's a quadratic if the initial velocity is not 0. And I personally don't like to solve quadratics, so I will usually go around like above and beyond to not do a quadratic. So I'm actually going to solve for v final first, v final in the y direction, and then I'll solve for time later. So, which is breaking my last rule that I said try to use your initial knowns, but I really don't like doing the quadratic formula. So if you have it in your calculator, it's easy enough, but I'll show you this method. Okay, so we're finding final velocity. We have initial velocity, acceleration, displacement. So we're going to use v final squared equals v initial squared plus 2a delta y. And we're solving for v final, so I'm not going to rewrite it because it's just a square root on both sides. And then our v initial is 7.7 meters per second. We square that. And then we add 2 times 9.8 meters per second squared times our, ooh, that's negative, times our delta y, which is negative 2 meters. So our v final in the y direction is negative. Once again, I have to make a decision if it's negative or positive, and it's going down, so I know that it's negative 9.9 meters per second. So that's my final velocity in the y direction. Now I can figure out time, and I'm going to do that using Vy equals V initial y plus acceleration times time. So we have the initial velocity is 7.7 meters per second, and then the acceleration is negative 9.8. Shoot. I forgot I'm solving for time. Okay, now we're solving for time. So we rearrange till we get time isolated. So we need to subtract initial velocity and then divide by acceleration. So V initial minus, sorry, V final minus V initial over acceleration. Now we can plug in numbers. V final is negative 9.9 meters per second. We subtract the initial, which is 7.7 meters per second. And then we divide by the acceleration, which is negative 9.8 meters per second squared. Really important here, if you get a negative time, you need to go back and check your answers, because, or your signs, because you probably have an incorrect sign in there, and that's going to give you an incorrect answer. All right, so I got 1.8 seconds. So there's my time. All right, we got lots more to solve for. Let's plug that in up here. So time equals 1.8 seconds. And we need to figure out how far it goes. So we're using delta x equals vx times t. And then we have 6.4 meters per second times 1.8 seconds. We should be paying attention to units here. Seconds cancel, we're left with meters, which is correct. I'm not always talking about that, but you should be paying attention to that. That gives you 11.5 meters. So the kid threw the ball 11.5 meters. All right, let's go back and reevaluate what we found here. We found the x max, we found the time. We do need to find the final velocity, so let's do that real fast. And for final velocity, we know that we have a velocity of 9.9 down, and then it's still going at this, I think it was 6.4, yeah, 6.4 meters per second to the right. That's the horizontal. So this is the final velocity that we're solving for. So we do Pythagorean theorem to find the velocity. And that gives us 11.8 meters per second. And then we have to find the angle. So we do the tan inverse of 9.9 divided by 6.4. And that gives us 57 degrees. So our answer here is V final equals 11.8 meters per second at 57 degrees below horizontal. Great. So there's that part. Wow, hard to make a circle. So now we need to find out how high it goes, which is the last piece. Now for this piece, we have a different time and a different situation. So let's kind of redo our XY chart here. We know that the initial velocity in the y direction is still whatever it was, 7.7 meters per second. The acceleration is still negative 9.8 meters per second squared. And but now our final velocity is going to be 0 because it is stopping at the top in the y direction. It's still moving the x direction. but it like stops moving up and starts moving down. And we need to find how far it goes. Shoot, I keep drawing X's. That's a lie. And this would be how far it goes above the person's head, right? So then we're going to use this equation. V final squared equals V initial squared plus 2a delta y. And we're going to solve for delta y. So we get delta y is equal to V final squared minus V initial squared. I don't know why I put F there. Y. V initial squared over 2a. And then we can plug in numbers. 7.7 squared. Oh, final 0. Goodness, I didn't even think about canceling that out. So the V final is 0. Okay, so we get negative 7.7 meters per second squared divided by 2 times negative 9.8 meters per second squared. And that gives us a delta y equal to 3 meters. Then we have to add the 2 meters for starting position because it started 2 meters off the ground. So we got 5 meters. And that's all.